In this video, we're going to talk about bond order and also bond length, and we're going to see how these two properties relate to one another. Now, bond order is simply the average number of bond pairs shared by two atoms in a molecule. And there's some real simple examples of this that we'll start with. If we look at the Lewis structure for nitrogen gas, N2, we're going to end up with something that looks like this. And in this case, the nitrogen-nitrogen bond order is 3 because we have a triple bond that we assign the value of 3 to, and we divide that by the number of nitrogen-nitrogen connections. So it would be the bond order is going to be 3 divided by 1, which is 3. And we're going to do this. We're going to assign a triple bond. We're going to assign that a value of 3. A double bond, that gets assigned the value of 2. And a single bond, as you can probably guess, that's going to be assigned the value of 1. In O2, if we draw the Lewis structure for oxygen gas, we end up getting something that looks like this for O2. And here we calculate the bond order for oxygen. We're going to assign the value of 2 for our double bond, and we're going to divide that by our single oxygen-oxygen connection. There's just one connection between the two atoms. And so that's going to give us a bond order of 2 for oxygen gas. If we do the same thing for fluorine, we get a Lewis structure that looks like this for F2. And once again, we're going to assign a value of 1 for the connection between the two fluorine atoms. And we're going to divide that by 1 because there's just one connection between the two atoms. And our bond order for fluorine ends up being 1. Now the bond length is basically the distance between the two nuclei that are involved in the bond. So that's just going to be the distance between the center of the two atoms involved in the connection, whatever it is, whether it's a triple bond, a double bond, or a single bond. And I'm going to go ahead and write the bond lengths that exist for these particular molecules. It's 109 picometers in nitrogen. It's 121 picometers in oxygen, and it's 144 picometers in fluorine. And so we see this sort of connection that as bond order increases, so as we go from a bond order of 1, which is single bond in character, to a double bond of 2, which is obviously double bond in character, to a bond order of 3, which of course is triple bond in character, we see that the bond length decreases. And that's also because the strength of these bonds increases in this direction. So you have a stronger bond here that's going to pull the atoms in a little tighter. Here you just have a double bond that's going to pull the the atoms into a medium extent. And in a single bond, that bond isn't quite so strong, and so the two atoms in the bond are a little further apart. There are some lists of these various bond lengths that you can find in Chapter 8 in a table. Now, these are simple examples. Let's do this for nitrate. We'll calculate the NO bond order in the nitrate ion. So I'm going to go ahead and take you through doing the Lewis structure for nitrate. The first thing we do is we determine the central atom, which is almost always listed first. Next thing that we're going to do is we're going to find the number of valence electrons that exist in the ion. So I have a nitrogen atom, and that's going to have 1, 2, 3, 4, 5 valence electrons. So I have 5 valence electrons times 1 nitrogen atom. That's a total of 5 valence electrons. Now we'll go to oxygen. Oxygen's going to have 1, 2, 3, 4, 5, 6 valence electrons. So for oxygen, there's 6 valence electrons times 3 of them. That's going to give me a total of 18 valence electrons from the 3 oxygen atoms. Then we have a negative charge here, so that's an electron. that we're actually going to add to the mix. There's one of those with a -1. So that's going to be a total of, we add that up, that's 24 valence electrons. Now we draw our central atom, which is nitrogen. We draw single bonds to all terminal atoms. And then we satisfy all terminal atoms with a stable octet. So this has 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And this one, 1, 2, 3, 4, 5, 6, 7, 8. I count how many valence electrons I've used total, 8, and 8 is 16, and another 8 is 24. So we've used them all up. If there were any left over, they would go on the central atom. Well, we know our terminal atoms are satisfied with an octet because we just gave them an octet. Now we check our central atom, and we notice that our central atom has 1, 2, 3, 4, 5, 6. Well, this needs 2 more. How do we fix that? Well, what we're going to do is we're going to move a lone pair of electrons on one of the oxygens, it doesn't matter which one. We're going to move that into a bond pair with the nitrogen atom. So it's going to look like this. We have our central nitrogen. Let's have 1, 2, 3, 4, 5, 6, 7, 8. Same with this one. And now this particular oxygen, we've moved these 2 electrons into the bond pair, so there's going to be a double bond here. And then these 2 electrons will stay here as a lone pair. These 2 electrons will stay here as a lone pair. And this has been moved into the bond, so I'm not going to draw that here. Now we're ready to calculate the bond order in nitrate. Because, of course, our nitrogen now feels like it has 8 valence electrons. So everything's satisfied here. This is a good Lewis structure. In this case, we're gonna give the value of 1 to this particular connection, because it's a single bond. We're going to give the value of 2 to this particular connection, because it's a double bond. And we're going to give the value of 3 to this particular connection, a value of 1 to this particular connection, because it's a single bond. So we're going to take 1 plus 2 plus 1, and we're going to divide that by our 3 nitrogen-oxygen connections to calculate our bond order. That's going to come out to 4 over 3. That's our bond order. So we'd say our bond order in the nitrate ion is going to be 1 1/3, which is about equal to 1.33. And so what this tells us is that we would expect the nitrogen-oxygen connection in nitrate, each of these actually, to experience a bond strength that's somewhere between a single bond and a double bond. The bond's going to be a little bit stronger than a single bond, but a little bit weaker than a double bond. And what we're going to need to recognize is, you might remember me telling you that these oxygen atoms, when they're surrounded by a nitrogen atom, these are absolutely identical. So again, it's not like you can tell the difference between one and another. Now, if this is the way that I draw the structure, such that one of the oxygens has a double bond and the other 2 have a single bond, well, then it would be the case that I can tell the difference between this oxygen atom and the other 2. Because, well, there's a double bond here to the nitrogen, and here there's only single bonds. And so we're going to start envisioning the case, if we see this kind of thing, with something with a bond order of 1.33, it's going to be as if this double bond here is actually sort of spread out. I'm going to draw dotted lines here over all 3. And in this case, if all of these bonds have a bond order of 1.33, then we're back to the case where we can't tell the difference between the 3 oxygen atoms that exist in nitrate. And this is going to end up being a better picture for what's going on in the nitrate ion than this one here. This is still an okay picture. This is an okay model, and we're going to use it sometimes. But this one gives us a little bit better idea of what's actually going on with the electrons in the nitrate ion.